Yeah. Welcome all. Dr. Ilya Valo is a head of the group Nano Electrochemistry Research Center at Jülich in Germany, and he received his MSc degree in materials electrochemistry in Sofia and PhD from physical chemistry of solids or solid state electrochemistry in Gießen, Germany. His research interests are concentrated on electrochemical and general physiochemical phenomena at nano and sub-nano scale levels. And he been working on electric double layer point defects, surface and interfaces with a focus on resistive switching memories, memoristors and neuromorphic devices, energy conversion and electrocatalysis. A special focus is set on a relationship between material chemistry, structures and properties, material design, and particular applications and functionalities. He had published more than 140 original research papers, edited 2 books, 6 book chapters, and holds 6 patents. The results of his groups were frequently reported in magazines, newspapers, and social media. Is editor of scientific reports, materials, and guest editor special issues of RSA, Wiley, and Elsevier journals on the topics such as nano electrochemistry, memoristors devices, and neuromorphic functionalities. He chaired 2018 Faraday's discussion meeting on new memory prodigies, memoristor phenomena, and neuromorphic applications, and is a co-initiator and co-organizer of International Conference of Memoristor Devices and a System, which is the largest and the most important annual conference on memoristic theory and application. So it's a great honor to have Dr. Ilya Valo here, and today he'll be talking on the topic materials and nanoionic process for control memoristic and neuromorphic functionalities. So once again, on behalf of the organizing committee, I welcome Dr. Ilya Valo for this session and to deliver his talk.
Okay. Is now okay? Can you hear me? Can you see the screen?
Yes, sir. Yes, it's okay. Visible.
Okay. First of all, thank you very much for inviting me to present this talk this day, and the organizers for making the conference, and also including this topic. I'll speak today about materials and nanoionic processes for memoristic and neuromorphic functionalities. First of all, what I'll speak about more detail today. First I will give you an impression about nanoionics-based memoristic technologies. This means I will explain a bit more about the nanoelectronics that is driven by nanoionics processes. Then I'll give you about an idea what are memoristors and electrochemical fundamentals of transmission, of generation and transmission of neural signals, and how memoristors mimic it. And then I'll come to the main part, which will show the relations between materials, processes, and device performance. So in the whole talk, this link between these materials, processes, and devices will be maybe the most important thing, as it allows us now to improve these devices and implement them into the industry and different applications. So memoristic devices and technologies, I'm not sure in how far the audience is familiar with memoristors, but I'll give a very short explanation without spending too much time. So memoristors are 2 terminal devices that allow for different resistances, and with these different resistances one can save some information or corresponding in digital format, like 0 and 1, or in analog format when you have different resistances for different that correspond to different states. Memoristor is coming from memory and resistor, and it was introduced by Leon Chua 1971 as theoretical element, and later on the last 20 decades this is one of the most hot topics within the new paradigms in memories or neuromorphic computing. Memoristors can be used for a variety of applications. They are devices. They are based on very simple electrochemical, very simple principle of operation, and that's why it can be also used for many applications like neuromorphic computing. IoT, the Internet of Things, artificial intelligence in satellites, in autonomous cars, and in healthcare. So it allows for very different functionalities, not only one functionality, but different functionalities, and its simplicity and multifunctions allowed to be used in many different fields. There are different types of memoristors. So the memoristor, as introduced by Leon Chu, is an ideal construct that it's not always absolutely correct in terms of ideality. So there is no ideal system that works as it must work. But at least memoristors are now considered as many, can be considered as many different systems. I'll show you now the resistive random access memories. So based on change in the resistance. So this resistive random access memory can have different physical origins for changing their resistive state and for their operation. One of it is the so-called redox RAM. It's redox reactions. They're based on electrochemical reactions within this device, and they can be ECM cells, electrochemical metallization memories, also called conductive bridge memories, or VCM, valence change memories, also called OXRAM, or TCM, which are thermochemical memories. All this, the name is somehow trying to express the basic principle that the device is working. You also, memoristors are also considered phase change memories, where you change the amorphous to crystalline state, which is resulting in different conductivity or different resistance. They can be compound or elemental form, magnetic random access memories, electronic random access memories, and nanotube random access memory based on van der Waals forces. So these are all different types of memoristors. Of course, they are not all included, but the most popular one, which are inorganic memories. And I will speak today about the left part, about the redox-based resistive memories, which are also well, I'll focus maybe on these first two, not on the thermochemical memory. I told you that this type of memories are based on electrochemical reactions and transport. So their structure is quite simple. So you have a thin film, some oxide, or I'll speak about this a bit later. So many different materials can be used for ion transporting solid. Even also liquid can be used and so on. And then you have two metal electrodes. One is typically inert, but not necessarily, and the other is active. And so you can change all these three components in the system to achieve different functionalities. And it is not only the individual components, so not only the electrodes and the solid electrode or the insulator, as you can call it also, but it is also the interfaces that are formed at the contact positions. And that's why it's not only the individual material, but also the combination of materials that predetermines the properties. And in fact, we can change many things in these cells. So we can change the active electrode material, we can change the counter electrode material, and we can change also the chemistry and the physics of the solid electrolyte. And I'll go in brief today on all three components. What results when you change one of these components that are important has been already demonstrated several years ago by one of our works. So depending on what kind of electrodes you use and what kind of electrolyte, you have different rate of the electrode reaction. In fact, the rate of this reaction that happens at this interface, oxidation or reduction, and also here. And also the transport properties of your material. You can have a different type of growth of the filament that short circuits the devices, and very different behavior. That's why it is important to change materials and see and make a roadmap on material design about memoristic devices in order to control their functionalities. Now I'm coming to the next topic, which is explaining why we use memoristors for neuromorphic computing, or for also for artificial synapses and even neurons. A very short introduction to biology of neurons. The normal neuron, the organic neuron that is in our body or in the cells of the plants and animals has a very precise balance at the both sides of the membrane of the cell. In the intracellular and extracellular liquid, you have different concentrations of potassium and calcium, potassium and sodium ions on both sides. The size here is corresponding to the concentration difference. So we have more sodium in the extracellular than into the intracellular liquid, and more potassium than here. But the concentration of sodium outside is the highest. So this chemistry outside and inside the cell is compensated by so-called Donan potential. So it is electrical potential that compensates the different chemistry. Naturally, in nature, everything tends to equilibrate. So the natural driving force is to equilibrate the concentration on both sides. Because this cannot happen, because we have some channels that are closed and it's not allowed. To compensate this chemical difference, an electrical potential is built, which is about 70 to 90 millivolt. At the moment, we have some electrical impulse that is, or any other kind of disturbance of this equilibrium, then this immediately results in change of the electrical potential. So if you change the potassium or sodium concentration outside or inside, the potential will change, the electrical potential will change. If you apply electrical potential outside, or some electrical potential is fired from one of the neurons, then it also changes. Of course, when it's more or less than this one, and this results in also chemical response. So it changes also this equilibrium. So this is a dynamical system which is balanced, is a balancing between electrical potential and chemical potential to maintain the general requirement for the electrochemical potential gradient to be equal to 0. And this type of potential, which is caused by different concentrations, is called diffusion potential. And this diffusion potential is responsible for this equilibrium. The electrical signal in a neuron can be transmitted if you achieve some threshold potential. After achieving this threshold potential, you cause, of course, this change in the concentrations. Then you have so-called depolarization, the action potential, repolarization, hyperpolarization, and here again achieving the resting potential. So you start at this point and you finish at that point, but this is the general potential distribution with time, which is responsible for transmission of neuron signals. The electrical force that is formed of this equilibrium is can be described from this equation, which is called which is the membrane equation. The membrane equation is a modification of the diffusion equation, and the Donald potential, which I told you is called this on the neuron side, is a modification of the membrane equation. So in fact, the basic fundamental is the diffusion equation, which is known from the classical electrochemistry, going through the membrane equation, and in biology it is further modified by so-called Donald potential equation. Because the fundamental is the same, I'll show you the same response in an artificial inorganic system. So here we have silver electrodes, a memoristic system, silver electrodes, germanium sulfide as electrolyte, and platinum as a counter electrode. So initially you see this shade around the electrode. This is because silver is chemically dissolved into the germanium selenide. You see this is corresponding to this situation. So we have silver ions which are dissolved within the electrolyte. Then we apply negative potential to the silver electrode, and you see after application of the potential, silver whiskers start to grow here. And you saw also the change in the morphology of the electrode, because you extract the dissolved ions, you extract them out of the material. And then exactly at this point, when the whiskers stop growing anymore, you switch the applied potential off, and you start measuring the voltage which is delivered by this cell. So this is like a battery. We call this nano battery. And you see what happens with the voltage which is generated by this cell. And in the same time, you see how silver whiskers start to dissolve back into the material. So this is the depolarization, this is the repolarization, and the hyperpolarization. And then with time, it takes a bit about 10 to maybe 20, 2,500 seconds to achieve the initial state. So the reason for this longer reaction time. So you see here is on a seconds scale, and here is on a millisecond scale. It's only the system we have selected. So you can select different systems, but this was most suitable for visualization of the whole process in this type of artificial neuron. And so in fact, here what happens here is that we start again to dissolve silver within the electrolyte. Of reason that we have the same fundament here is again the diffusion equation, which is responsible for the behavior of the cell. So initially you change this equilibrium situation, you extract ions, then they are coming back, and of this reason you see also this type of time distribution, the potential time distribution into the artificial cell. So this is the reason we are using memoristic devices for neuromorphic computing, because they emulate very nicely, or very well, based on the same principle, the operation way of the biological neurons. Now I'm coming to the materials and what is their role in designing artificial synapses. Electrode materials, or especially active electrode materials, are used very largely in many different materials. So you can see all these colored metals elements are used as electrodes. Of course, mainly popular in the electrochemical metallization cells, or CBRAMs, are copper and silver, but many others are used. And for the other cells, you have many different materials. In fact, the choice of particular metal is only limited by its properties, so how electrochemically active it is, and how fast the ions can diffuse within the matrix, the electrolyte matrix. So when you change the different materials, you see the different behavior of the whole device. Here in the upper figure, you see copper. So we use copper as active electrode, and each peak corresponds to a reaction of copper. So you see the difference compared to silver, where silver is, of course, different element and has different electrochemical behavior. And you see it's not only the shape of the sweep, but it's also the current densities, and it's also the voltage ranges. You see, to work with copper, you need to apply voltage up to 1.5 volts in one direction, up to -2 volts in the other direction. For silver, you need much lower voltages to operate. So you need about 0.2, 0.3, and here you can 0.6. So this gives you an impression what is the influence of the active electrode on the device behavior. The same applies for the counter electrode. The counter electrode is usually inert material, which is not directly reacting and is not providing any mobile ions. But its catalytic activity is important in that case, because it serves as a base that the filament can grow. And you see that different noble materials, platinum, iridium, and ruthenium, they have different catalytic activity. You see how earlier iridium iridium promotes the current, and platinum, which is also inert element, it starts much later. So this means that you need a much lower voltage or much less energy to apply, and iridium will allow reaction, whereas platinum will not. So and I also provide for comparison some other materials that are used for memoristic devices. Titanium nitride is electronically conductive material, or ITO as transparent conductor. So all of them give different responses and different possibility to arrange the reaction time, and also the voltage that you need to apply in order to operate the cell and the device. And here you see the real operation. So in the previous slide, you have seen only the electrochemical responses without switching, without complete function. And here you see the device kinetics, already switching kinetics, which means changing the resistance state with the purpose of either neuromorphic or memory functions. You see as higher is the catalytic activity of the electrode material, of the counter electrode material, the higher is the speed of switching, the speed rate, and the rate of switching. The lower is the time. And when you go to a lower catalytic activity, the time for reaction is much slower. And if you take, for example, materials which oxidize and provide even higher resistance barrier, like tantalum, which can oxidize, you see that the results are much slower. The switching kinetics is much slower compared to, in that case, it's ruthenium that is given for comparison, orders of magnitude. So changing different electrode materials is allowing us for changing the reaction rate and also the device operation time by orders of magnitude, not only a few, it's really by orders of magnitude. So I explained in the previous slides a bit more. It was about the electrochemical metallization memories, where metallic filaments are formed, and metallic ions from it are responsible for the switching process. But in the VCM, in oxygen change memories, in RAM or valence change memories, you also see electrochemical reaction. This time they are related often to oxygen within, which is typically used or extracted from the solid electrolyte material, or naturally absorbed moisture or protons, which are coming or almost unavoidable in most of the preparation processes and steps during the preparation of the devices. So you see, after the initial sweep here, in the one VCM device. So the initial sweep is almost no current. Simply sweeping, you see that the current starts to increase, and this peak here is indicating the electrochemical reaction. If you zoom in more details here, you see the electrochemical reactions happening. And if you continue with cycling for more time, you see also bubbles from gas that formed. So you don't need specially to expose to some special moisture level. It's enough, let's say during the ALD process, there are enough protons that are within the device, and they can be, they can form, let's say, hydrogen, or simply during device preparation steps, you have some exposure to moisture, or even environmental moisture is enough to penetrate after 10 to 15 seconds, even in encapsulated devices, because most of the encapsulation is not sufficient to stop the natural penetration of moisture. And you can see such type of devices show when you expose them to extreme atmosphere. So it's about 90% humidity, just to accelerate the processes. You see that if you apply negative voltage, you form hydrogen, which is characterized by some kind of explosion from the bottom of the device. If you apply positive voltage to the electrode, you see with time how oxygen starts to form. it starts to form from the edges because the current density there is the highest. But when you cycle more and more cycles, you see the whole area is covered by oxygen. So in fact, it depends not only the electrode materials, but also the environment. Also depends on whether material is absorbing moisture or not absorbing moisture, or whether it has protons or not, and how easy it offers its oxygen from the lattice to be oxidized or reduced. Now, the fact that we have different redox reaction, in fact, it's helping also to take to determine which reactions we would like to involve or not to involve, and this is the ways to control the voltage magnitude. So in electrochemistry, there is so-called standard electrode potential table, or standard electrode potential order, which is saying when one redox reaction will take place at which potential, what conditions, what energy conditions. And negative potentials have elements that oxidize very easy, such like, for example, tantalum or lithium. They have a very negative potential. And on the other hand side, you have the noble materials, so-called noble materials, which have a positive potential, and they are not oxidized easy. This is like, for example, gold is a noble metal, is noble, but also oxygen. So this means for the devices that we can determine which reaction may take place or may not take place. If we apply positive bias, the first reaction that will happen will be oxidation of tantalum. So tantalum will be oxidized to tantalum X plus, because it has a very negative standard electrode potential. So even small applied voltage will cause oxidation of tantalum. But if the voltage is small enough, none of the other reactions will take place. So we can avoid that reaction, the reaction of water or OH or oxygen takes place simply by applying a lower potential, lower positive potential. Then if we increase the positive potential, then the second reaction, this reaction will take place. If we further increase the voltage, we'll also have this reaction at the end, at very high positive potentials, oxygen will be oxidized to form oxygen molecule. The same applies for the reduction, but in the other direction. Reduced will be first the elements with the most positive potential. In that case, if we have oxygen, molecular or atomic oxygen, this will be the reaction that will first take place. Then increasing the negative voltage, we'll start to reduce oxygen in the presence of moisture, or then we'll reduce water. And at the very end, when we apply very, very high negative voltages, we'll reduce tantalum ions to form tantalum metal. So this means that the voltage magnitude determines not only the reaction rate, because as higher the voltage, as higher the reaction rate, but it also changes, can decide where to which voltage to apply in order to stop or accelerate one particular reaction. So this is an additional way of control of this of the reactions. Another way to control the reaction is selecting the Schottky type of the type of contact. If the discussion up to now was applying for ohmic type of contact, but many metals have a Schottky type of barrier that they form with the oxide. And in this case, this is another degree of freedom to decide which material to take, as it can limit the electrons that can penetrate within the material, and this way also to change the device performance. Now, I spent too much time on the electrodes, and the time is a bit limited to 30 minutes. So I'm going to the next important component of memoristic devices, and this is the materials that are used for electrolytes. So they are called electrolytes, but in fact they are typically considered on a macroscopic level insulators, but as you see from this figure, this slide, almost all materials are used as ion transporting solid, or as materials that are used to mediate ions and be used for switching. These are 1D materials, so nanowires, nanotubes, 2D materials, many different materials have been used for memoristic devices. 3D materials, of course, thin films, organics, polymers, bio-inspired materials like eggshell, orange peel. Even one colleague has demonstrated functionalities with using Nutella. And of course, a single molecule can also switch 0D, so to say. So many different materials are used. So it's not a question which material can switch. Almost all materials switch that have been tested. The question is which material switch is reliable and provides the functionalities that we aim to. And now I'm coming to the part that I have told you, the interface between the two contacting phases. So we have seen we have very different materials that can be used for transporting solids. We have very different electrodes that we can use. And now I'm coming to the most important part, how to control this, combining all these components. So first, I'm showing you the Gibbs interface concept that the electrochemists called, in fact, the formation of electrochemical double layer, and the physicists called it space charge layer. It's actually the same. So you have a metallic phase, you have electrolyte phase, and you have the interface. Within the metallic phase, on the macroscopic level, you don't have any gradients. So you have constant chemical composition, you don't have a gradient of the potential, of electrical potential, everything is constant. But on the interface, exactly what happens at the site of the membrane of the neuron, you have a gradient of the chemical potential. This is usually the concentration, and you have a gradient to compensate this. You have a gradient of the electrical potential. So in fact, the field which is generated within this electrical double layer is reflecting the chemical forces on the both sides. And the fields that are generated here are in the range of 10 to 8 volts per centimeter. So what happens when we take this interface and make it our electrolyte? So this is actually what we mostly make with memoristic devices. We don't have a classical situation, but we have this situation. We take the interface, and our interface is so to say, the electrolyte. And it depends, of course, on the concentration. So it depends how many ions we have within this interface. If we have a few ions, let's say a black is zero. Of course, this is calculated values, so absolute zero you cannot have, or 150 ppm. Then you have overlapping space charge layers. So this means that your whole material is a space charge layer. And then you see how potential goes through. And also here. When the concentration is increased to 1,500 or 15,000 ppm, then you start to go back to the classical situation where we don't, which I have shown in the previous slide, where you have almost constant potential within the electrolyte. So everything depends. It's not only a matter of size, but also a matter of concentration of mobile charges. And in addition to this, you see here that the electrodes are different because they are different. They're chemical asymmetry, which is intrinsically incorporated in the cell. You have internal voltage, which is formed and which drives ions to move in one or other direction until it reaches steady state. And what is the difference between these two situations when you have a low concentration of mobile species and high concentration of mobile species? So when we have a low concentration, we have a field acceleration kinetics. This means that the electric field, it's directly influencing the transport process, and it's much faster. So you see the equation here. Important is that you have exponential dependence of the current, whereas normally you don't have this exponential dependence. This is only the classical electrochemical reaction rate. Here the interfaces, but here the transport is driven solely by the Fickian diffusion. So it's a normal diffusion process which is driven from the concentration differences. Here you have field accelerated kinetics, and the mobility of ions exponentially dependent on the applied field, and also depends on the charge of the ion. So if you have oxidation state which is higher, let's say if tantalum has 5+, it will be stronger accelerated compared to if you have an electron which has a single charge. So the electric field is differently accelerating the different mobile charges. The situation is interesting when you have the intermediate concentration, which is neither too low, neither too high, because in this case, the internal electromotive force results in splitting the charges. So they're not homogeneously distributed within your material, but they formed enriched and depletion zones, which also change the device behavior, and also they form some kind of so-called electrochemical capacitance. So additionally to the classical physical capacitance that is in fact determined from the matrix, you can also have intrinsic separation of charges, which will lead to formation of electrochemical capacitance. So what is the influence of different ions? So we have mobile and immobile ions that, or different charges that can be used into the material. So the mobile charges are, let's say, protons. They are silver, let's say silver, copper, or oxygen when they move. And of course, we don't have to forget the compensating defects. Many colleagues I have seen are saying, okay, we add protons or we add silver or we add copper ions into the material and it works. We cannot add simply one ion. We need to also combine the counter ion. So they always come in combination. So in fact, we have a situation where we can introduce additionally into the material mobile ions or extract them. This is has some disadvantages. So we can have accumulation or depletion of mobile charges due to the operation of the device, exposure to atmosphere, changes in the difference in the temperature, changing in the chemical composition. So you may have chemically reacting electrode and electrolyte. The accumulation of volatile impurities leads to elimination of the acceleration effect of the electrical double layer, which I told you is the field acceleration effect. It lowers the rate in the transport, and it leads to short circuits and high power consumption. Of course, with time, you can change from one situation to another, but it's much easier to incorporate more ions than to extract them all. So that's why the devices usually degrade with time, because you can never extract all the ions you have incorporated within them. What about impurities or dopants that you intentionally incorporate into your material? So they have the advantage that they cannot move, they cannot be extracted, so their concentration remains constant. They cannot accumulate or deplete, and they can use different charge compensation. So you can different ions may compensate their charge. What is specific for the main ions, the immobile ions? They are forming bonds with the mobile ions. For example, if you use gallium or aluminium, they form different bonds to copper, and depending on this, copper will diffuse faster or slower. So this is the main importance of the doping or of impurities, that they determine how fast the ions will move compared to the undoped matrix. So additional ions or doping or doping ions or impurities, they change the classical capacitance of the cell, because they form dipoles, but also they can change the acceleration effect and diffusion and migration rate, because they hold stronger the ions. But on the other hand side, as you'll see, they stabilize the states, they stabilize the filament. Just to show you the effect of impurities, of doping and using different materials. So you see, this is a pure silicon oxide we have used as a switching matrix. And this is doped by different materials. So you see at the same voltage, you have orders of magnitude faster switching compared between materials with doping and with the higher concentration of mobile charges and with almost no additional concentration of additional charges. So it's orders of magnitude. At very high voltages, both come together because the field is so high that the field acceleration applies to all raw materials. And we were able to achieve the fastest switching practically for ECM, for electrochemical memories, electrochemical metallization memories of about 1 nanosecond. We were able also to, at least this is the resolution. We are at the moment working to detect faster switching, but at the moment we can detect this 1.4 nanoseconds, which is orders of magnitude faster compared to doped materials. So I'll give you also in the last slides the impression what is the influence of these additional charges, mobile and immobile, to the matrix and how they influence the neuromorphic functionalities. So here is a train pulse to apply to the voltage. This is with 100 microseconds and a magnitude, and the magnitude is of about 0.8 volt. So you see initially the first pulses doesn't change anything. So this is, we interpret this as classical capacitance determined solely by the matrix. However, with time, what happens is that the current starts to increase. I told you that we have accumulation of ions, and accumulation of ions results in changing the electrochemical capacitance, which helps the cell to switch, in fact, to form the filament until we reach this situation where we have the filament formed in the green area. So the initial phase is controlled by the immobile dopants or impurities. So its permanent influence depends on the ionic charge and bond strength. It's the classical capacitance. We have electrochemical capacitance, additional component, which is determined by the mobile dopants. It's a temporal influence. It can be changed with time, depends on the charge and bond strength and mobility, the electrochemical capacitance. So using these two effects in addition to the electromotive force and applied external voltage, you can control better your neuromorphic device. And it's only a demonstration, the last two slides, how it works. So with a very pure material, very pure silicon oxide, you see a very fast switching because material is very fast. Is not providing any problems for copper ions to diffuse, but it's also the filament is very unstable at this current compliance. So at low current compliance, it's immediately switching off. So fast switching, but unstable filaments. On the other hand side, when you use dopants, then you see for gallium and aluminum, sorry, I have put both aluminum. So you see that the different time for switching, but also the different time for depression, for different time for reset, for forgetting, so to say. So you see the very short pulses, none of it forgets, but one is switching faster than the other. But then where the bond is a bit less stronger, weaker, then you have already forgetting. Here you forget, and here you still don't forget. And when you go to a very long pulses, then you see that the forgetting is very fast, and here it's still not very fast. So in fact, what you can conclude from these experiments is that you can design the sensitivity of your artificial neuron, so how sensitive it should be to electric pulses, and you can decide whether you want it to learn fast and forget fast, or learn fast and remember forever, or how fast to learn, how fast to forget. All these parameters can be adjusted by materials design in addition to the train pulses. So I'm at the end of my talk. I think it took a bit more time that I have planned. So my conclusion and my message to you would be that nanoelectronics, the modern nanoelectronics need nanoionic processes to be controlled, more precise, and allow for more applications and more broad spectrum of applications. The relations between material properties and device performance is essential for the development of the research and applications, and fundamental understandings of the elementary processes is a key for further development of this new technology. I would thank to collaborators and co-workers, and would like to thank you for your attention. Thank you very much.
So, thank you so much, Dr. Ilya. We have a couple of questions. First question is from Ramesh. Question is this: are these lateral devices or vertical devices, and how good is the interface? And the last piece of the question is: would love to know if we make an atomically precise interface, how would be the device perform?
Yes. What I have shown were vertical devices. Some of the figures that were given on the example of horizontal devices, but most of the results that I have shown are vertical devices. In the lateral devices, they are not so easy to be scaled to nanometer size. So it's possible, but it's not so trivial. So for most of the studies, we are using vertical devices. Now the second question, how good is the interface? You can produce it atomically flat, but to our experience, it is not hold this quality. This atomically flat surface is held only within maybe the next minutes or half an hour, and then so metal and layer and oxide layer or switching layer interact with each other, and they form an interface. This is a problem which I haven't got the time to discuss, but you form immediately interfaces, and these interfaces are typically within 1 to 3 nanometers, up to 3 nanometers. You can change your initial interface and exchange of materials and charge between electrode and electrolyte. What is the influence on the performance? Of course, we found that these intermediate interfaces, so in fact, the question is quite good, and exactly these interfaces usually control the device performance. So if you have a stable interfaces, if you can stabilize them, then you may predict your device performance. The large variability of many devices is related very often to the process to the fact that you form interfaces. They may block completely your exchange. Okay, the second were the answer okay?
Was yes, yes, okay? Yes, yeah. Fine, okay. There's a few more questions. I'll just read out. Yes. Is the interface sharp and uniform thickness? If not, what are the consequences?
Okay, I think I have answered actually with the first question. It's not sharp. It's not the thickness is not always uniform, I have to say. And this memoristic devices, one of the biggest problems that they suffer is the large variability. And one of the problems for the variability is exactly if the devices are too thin. What we can do against this is to increase the device thickness. So if you use, let's say, 5 nanometer switching layer, and your interface layer that forms is about 1 nanometer or 2 nanometers, of course you have a problem, because you don't have a problem, you simply have different material that you have deposit. So if you deposit maybe 50 nanometers and you have 1 nanometer interface, then the influence of the interface will be a bit diminished, but not completely neglected. So interfaces are, for me, one of the way to to control precisely the device functionalities, and not the switching material itself, but the interfaces are more important.
So there's one more last question by Dr. Gagi Reina.
Yes.
Question is, does the thickness of the intermediate layer affect the switching behavior?
Yes, West intermediate layer is affecting the switching behavior because it is a different composition. It has different transport properties, and for me, the intermediate layers are most important. So interface layers and intermediate barriers, they are in fact responsible for any deviations. And if there is something we can do at the moment to improve the variability, this is to better control interfaces and such type of intermediate layers that form, because usually many people even don't realize it. I think this is yes.
So on behalf of the organizing committee, we would like to express our sincere thanks to Dr. Ella, and again, thanks to the audience as well. Thank you so much.
Thank you also very much for inviting me, and
thank you, Dr. Ella. This Grace here, I couldn't join at the beginning. Thank you.
Oh,
yeah. Thank you very much. Yeah, thank you very much for the session.
Thank you.
Thank you. Yeah.
Have a nice day.
Have a nice day. So we can continue with the next session. Hi, Dr. Harry.
Hello.
Yeah, hi. How are you?
Very well, thank you. Yourself?
Thank you. Yeah. Dr. Vella, can you stop sharing your presentation? Dr. Vella? Yeah, thank you. Yeah, Dr. Harry, I think we can get started. Before that, I'll introduce my team to you. We have here Dr. Vasudevan, Dean School of Mechanical Engineering, VIT University, India, who will be chairing your session. Dr. Vasudevan is Dr. Harry Ruda, and he'll be giving a talk on optoelectronics. And this is a team, myself, Nirmala, Dr. Vimala, Dr. Velmurugan. So thank you once again for accepting our invitation and honoring this event. So may I request Dr. Vasudevan to take over and introduce the speaker for today. Thank you.
Yeah, thank you, Dr. Nirmala. Hello, Dr. Hari, how are you? Thank you
Very
much
well,
for joining.
you.
Yeah, great to hear. Thank you so much. Good evening to all of you. On behalf of CNR and VIT, I would like to welcome all of you for this World Nano Congress on Advanced Science and Technology, particularly this innovative talk on prospects for nanowire, nano optoelectronics and sensing, which is going to be delivered by Dr. Harry Ruda. Before going to the talk, just I would like to briefly introduce Dr. Harry. Dr. Harry is a Stanley Mick Chair Professor in Nanotechnology at the University of Toronto and Director for the Center for Advanced Nanotechnology, which is Canada's first Center for Nanotechnology. After obtaining his BSc from Imperial College in 1979, he joined in MIT. From 1979 to 1982, he worked on the optical and transport properties of 2,6-based infrared detector materials and obtained his PhD in 1982. Between 1982 and 1984, he developed one of the first theories for electron transport in selectively doped two-dimensional electron gas heterostructures while working as an IBM postdoctoral fellow. Then he joined 3M Corporation as a senior scientist while being a key member of the Blue Laser Beam. In 1989, he joined the University of Toronto, rising through the ranks to his current full professor appointment. Professor Ruda has published over 290 publications in international reputed journals with over 7,726 citations and having a index of 43. He has co-authored four books and has 14 patents. Professor Ruda's research interests focus on optoelectronic nanostructures with application in areas such as biosensing and information technology. Harry Ruda serves on the National Science Engineering Council of Canada and on other government panels, including those of the DOE, EPA, NSF in the US, and the RAE and EPSRC in UK. He serves on the International Advisory Board of the National University of Science and Technology in Moscow as a board member of Canadian Solar Inclusive. He has also served on the editorial boards of Journal of Applied Physics, Applied Physics Letters, Journal of Nanoscience and Technology, Journal of Material Science, Materials in Electronics, Nanotechnology Research Letters, Nano Micro Letters, and is currently the chief editor of IED series. He is a fellow of the Royal Society of Canada, fellow of Institute of Physics, fellow of the Institute of Nanotechnology, fellow of the Institution of Engineering Technology, and fellow of the Canadian Academy of Engineering. With this brief introduction, once again, I would like to welcome Dr. Harry Ruda to deliver the talk. I request participants, feel free to unmute your mic and raise your doubts, or you can chat your questions, then we'll clarify once the presentation is over. Thank you very much, Dr. Harry. Now you can start your presentation. Thank you very much.
Thank you so much for that very kind introduction. And also thank you to the organizers, to Professor Grace, Namila Grace, for inviting me. It's a real honor to be here, and thank you once again for that. So today, let me just move this thing out of the way, sorry. Just moving the bar off the screen slightly. There we go, good. So today I'm going to be talking a little bit about some of our work on nanowire optoelectronics as well as application to sensing. And I'll begin just with a brief section on nanowire basics. I'll then go on and talk about, as I said, the topic of nanowire optoelectronics, focusing on two things, light emitters and light detectors. And then in the third section I'll talk about nanowire sensors, particularly for biochemical sensing, in two paradigms, the optical approach and our work on the electrical approach. So I guess here we go. Let me just, there we go. Okay, so the first question in terms of the basics are what are nanowires, and why do we study them, and why do we make them, how do we make them? So one thing is when you look at nanowires, and if you look at this, let me see if I can get the pointer. You know what, I think I'll leave it as it is. When we look at the nanowire picture here on the right, you'll see that these are incredibly thin and long structures. They're the order of tens of nanometers, and one can grow them basically indefinitely, tens of microns long. So one has a degree of freedom, a dimensional degree of freedom in these materials that one doesn't normally have. Secondly, if you look at that same picture, that SEM micrograph with the long hairs sticking up, you'll see that the nanowires you're looking at are actually indium arsenide. The substrate's gallium arsenide, and those are highly mismatched. It's over 7% mismatched, and clearly lattice mismatch is not a limiting factor there. So in fact one can grow quite dissimilar materials on each other. So that means that one has a materials degree of freedom in these systems. You have both a dimensional degree of freedom and a materials degree of freedom in these nanowire systems. And sorry, just push this up. And so that means that you can design materials with appropriate dimensions and appropriate materials to access exceptional properties, things like quantum confinement, strong excitonic effect, strong dielectric confinement, and so forth. And I'll talk about those as we go through the talk. Also, because these are such small structures, in principle you can make miniaturized devices such as miniaturized sensors, single photon sources that go in the body, etc. So there's a lot of opportunities in these systems. And I didn't mention it, but these wires, such as the ones shown in the micrograph, are also single crystal structures, as you can see from the high resolution TEM in the bottom figure. So let me just touch on that issue of lattice mismatch and put it into perspective. I'd said in the previous micrograph that we were talking about indium arsenide on gallium arsenide. If you tried to grow planar structures, planar thin film structure by layer upon layer growth of gallium arsenide and indium arsenide, after 1.6 monolayers on average, or around half a nanometer, you'd end up with so-called island formation by the Stranz-Nekrasnikov growth mechanism, which is shown in the middle of the page. However, with nanowires, you can grow for tens of nanometers up to 60, 70 nanometers before you'll see any effect of that strain in the same system. So what's going on, and if you're looking on the left, what's going on, for example, the case of indium arsenide as the initial nanowire, and then we change the growth longitudinally to indium antimonide. What you can see is that those wires that are growing without constraint of material around them. So when there's strain, they can change their dimensions to reflect that additional strain energy. And indeed, if you look at the indium antimonide on top of the indium arsenide, you'll see that it's actually sort of blown up a little bit like a candle on top of or a match on top of a matchstick. And so that's the point, is that you have this ability to accommodate that strain by changing dimensions, which you don't have if you're trying to register a plane of atoms with every atom in configuration with its neighbor above its head in planar growth. So, and also this figure where I showed the indium antimonide, indium arsenide, shows that one can in fact modulate growth. So we can actually grow both inline heterostructures or longitudinal heterostructures as shown there, or we could do radial heterostructures, which we've used to control passivation or passivate surface states on the surface of these wires. So the next question, of course, is how do we make them? And here I've shown the original paper from Wagner and Ellis back in the 60s, 64, where they uncovered the so-called VLS mechanism, the vapor liquid solid mechanism, which is at the heart of growing nanowires. Now, when in their paper, they were focused on microscale structures. They called them whiskers, but they were microscale whiskers. And at that time, there was no sort of focus on the nanoscale, and we were one of the first in 1997, the paper beneath, to adapt what they did. But as the ideas are their ideas, and I'll explain how this mechanism works. So essentially, if you look in the red circle, you'll see there's a droplet of catalyst sitting on a substrate, and at the growth temperature that catalyst should be liquid in the liquid phase, and it should have a sparing solubility for add atoms from the vapor phase. So the idea is atoms from the vapor, for example, say it was silicon atoms from the vapor would impinge on the surface of this catalyst. They would be, since it's sparingly soluble, the silicon in that, for example, gold catalyst, they would be adsorbed, and we would build up a concentration until supersaturation of silicon in that gold was achieved, at which point they would want to precipitate out to relieve the supersaturation. And where would they do it? They'd do it at the low energy solid to liquid interface on the plane beneath. And that would carry up the liquid droplet like a candle, as shown in the right figure of their paper. And since the catalyst has not been consumed, it can effectively go on indefinitely, the wire growing, using that liquid phase, intermediate liquid phase, to mediate between the vapor and the solid, hence vapor liquid solid, and get growth. And in practice, how we do it is, if you look on the left micrograph top, you'll see a thin film of gold, a few nanometers, has been heated, and it self-assembles into islands of gold, from which, for example, if it's indium antimonide or indium arsenide, those add atoms are absorbed in those droplets, and the growth beneath, which shows those nanowires growing effectively indefinitely, occurs. So that's the growth process. Now, I mentioned about properties, so very briefly, when you have structures that are, within or smaller than the de Broglie wavelength, then you get quantization. You can see the standard states. If you imagine these are like these wires are sitting in a vacuum, for example, well, then there's a hard wall potential. So you get a very standard wave functions as shown on the top right. And for, say, gallium arsenide nanowires, you'd have band structure you could predict, and it would be exactly as you would observe, with approximately 1 upon d squared dependence, or radius diameter dependence for the band gap. But more interestingly, on the left, you'll see that the exterior dielectric constant, that medium, matters. So if, for example, it's in air, then the dielectric contrast between the wire, with its high refractive index or high dielectric constant, and air, causes electric fields to concentrate in the wire. and that raises single particle energies. Call that dielectric confinement, and we're going to see how that can be used very nicely in nanowire structures for things like sensing. The very last point I want to bring your attention to before I get into the talk, in terms of this background information, is screening. So the screening is the idea that if we embed, for example, a positive test charge in a conducting medium, then the carriers in the medium around redistribute to screen off that charge, screen off its internal electric field by compensating the charge of that bare test charge. In 3D, you can collect charges from everywhere, and you can very efficiently screen that test charge, which means that the screening lengths are very short. In a nanowire, if we're talking about a thin nanowire, where we're now in quasi-one-dimensional transport, because we've got confinement in the radial directions, then it means that to look for a carrier, the carrier can only come from the longitudinal direction of the wire. And so we have to go a long way to find a sufficient number of charges to screen off the test charge, which means that screening lengths are very long, or screening is very poor compared to the bulk. And that, in the sensing section I'm going to show you, is a key to getting very, very sensitive sensors. Okay, so let me now begin the talk, and I'm going to begin with the optoelectronics section. This is section 2, and the optical data that I'll be reporting on comes from our confocal micro-PL system, which is shown schematically here. And the key points I want to draw your attention to are: we're using an ultra-fast femtosecond laser system. We can tune the wavelengths, and we can also frequency double them with the harmonic generator. We can collect or do time resolved studies with the street camera, and we can do these measurements at very low temperatures. And lastly, with the confocal setup, we can look at individual nanowires and study along their length and so forth. And the confocal setup is shown on the bench here, and some of the key things are the pinhole, which is enabling us to essentially use that pinhole to scan and look for individual features and parts of wires. In fact, we reported some work where we put wires on TM grids, and we looked at heterostructured wires, and we could actually get luminescence from different parts of the wire and correlate that with the TM. I won't be talking about that today, but I'm just saying that's the kind of the capability of a system like this. And this is just another detail of the cryostat, which we pump down to 1.6 Kelvin. All right, so as a change of pace from the indium arsenide I've been talking about, and indium antimonide, I thought I'd talk a little bit about zinc selenide. And it's an interesting material, optoelectronic material, direct bandgap material, and interestingly, you can grow it very pure. It's single crystal, as you can see from the insert top. But by changing the stoichiometry of the environment, that is the ratio of the zinc to selenium partial pressure in the vapor, we can change the outcome of the luminescence, the photoluminescence. So if we want to make a laser that's one color or a laser that's another, we can do that, because this is luminescence. Obviously, this is radiative recombination, so this is light being given off on excitation of this material. So when we grow under zinc-rich conditions, a zinc to selenium ratio greater than 1, typically 5 in this case, we're dominated by band edge luminescence. 470 is the band gap, and you can see, in fact, donor bound exciton emission near the band edge. On the other hand, if we were to adjust with the same ratio back to selenium to zinc, 5 to 1, we'd end up with dominant deep level emission, radiative deep level emission, which is this red band shown on the bottom of the figure. And the blue band, which I showed you earlier, has been quenched. And the red band is due to, the two peaks in the red band are due to donor-acceptor pair recombination. So this is in fact due to native defects in the material. And just to put this, rather than kind of go through the complete analysis with you, because we don't really have time, and I just wanted to draw some attention to what's going on in these systems. The near band edge emission, as I said, is donor acceptor pair recombination, and it involves the zinc interstitial as the principal donor. The deep level emission, the red band, is also due to the same set donors, the zinc interstitial donors, but the acceptors are now zinc vacancies, singly and doubly charged ionized vacancies. So you have a Frankel equilibrium that's controlling the deep level emission, the red emission, whereas you have donor acceptor pair emission just involving the zinc interstitials for the near band edge. So let's have a look here at selenium rich, the selenium rich case where there's that dominant deep level emission. And by tuning the intensity of the light, you can tune the efficiency of recombination and the sampling of pairs of these donor acceptor pairs. And the reason is effectively the filling of, or the Coulomb potential, and that Coulomb potential goes with the distance, and so we're kind of sampling through distances. And when you do the analysis, you can see that the principal peak, the peak on the right there, is due to the doubly ionized Frankel pairs, and it has its peak at a separation of around 2 nanometers at a concentration of around 3×10⁹ per centimeter cubed, and that's what's dominating that red band. The secondary peak, due to singly ionized, or the first ionization state of those pairs, is the first peak on the left. Right, so that's kind of what's behind this story. So how can we rationalize what's going on here? Well, if you think of this graph here in the middle of the page, it's showing as an axis the selenium partial pressure increasing to the right. And when we do that, then we're going to be increasing if you kind of go through a Kroger-Vink analysis, we would be increasing the vacant zinc concentration, both singly and doubly ionized. At the same time, by increasing the selenium pressure, we would be also decreasing the zinc interstitial concentration. Which means that if we're looking at a strongly rich, zinc-rich condition on the left of this diagram, then we have quenched off the zinc vacancy concentration, and really the only defects, native defects in the system of note are the zinc interstitials. And that's why the donor-bound exton emission, involving just that donor, the zinc interstitial donor, was responsible for the blue emission. On the other side of the diagram, and remember these lines, I didn't say, but the vertical axis when you do this Kroger-Vink thing is actually a logarithmic scale. So these are exponential type of dependencies. On the right side, in the selenium-rich condition, you can see that there's comparable type concentrations of both defects, and that's why donor-acceptor pair recombination comes into play on the right of the diagram. So can we put this story together? Well, let's start just to finish that on the selenium-rich. And if you look at and what I didn't mention is we also looked at taking these single nanowires and putting contacts on them. And if you look at the carrier concentration, in fact, the carrier concentration is also in the 10 to the 19 or high 10 to the 19 kind of numbers. And obviously then the wires are highly compensated, as you'd expect, by having roughly equal concentrations of donors and acceptors. And it's typical, believe it or not, of MBE grown thin films, which all follow along that same 0.8 line, roughly speaking, of compensation ratio. That is, the ratio between the ionized acceptors and donors is roughly 0.8, which means that these materials are highly self-compensated. And it's showing up in transport, and it shows up in the optical response. That was the main point from this slide. So now comes to the $1,000 question: can one engineer a response or a color one would like? And the answer is, if this is the mechanism, surely one could. So if we would start with a zinc-rich grown nanowire, which is dominated by the blue emission, let's say we take it and we put it back and in the chamber and we anneal it in a selenium-rich atmosphere for 20 minutes. You see the left figure emerges. We've quenched off that blue emission, and we now have dominant red emission from the donor-acceptor pairs. And if we would take that same wire again and re-anneal it in zinc, we would lose the deep level emission, and we would regain the blue emission. So it's totally reversible. And clearly there's movement of native defects in this Frankel equilibrium. And so in order to put some meat on the bones, as we say. We did a time temperature set of annealing experiments shown on the right here, and we've plotted the ratio of the near band edge to deep emission luminescence ratio, and you can see that we can very nicely fit that using a simple radial indiffusion model for the zinc essentially vapor coming into the wire or leaving the wire through radial diffusion. And all of those curves fit with a activation energy of around 0.6 of an electron volt. And that actually corresponds exactly to well-known data from, old data on the diffusion coefficient for zinc in zinc selenide. So we can explain everything essentially in that regard. And just to finish, the last part of this puzzle would be those vacancies. And so if you do positron annihilation spectroscopy, which is looking at positrons being trapped on the vacant zinc acceptors through the S parameter, as shown in this figure here, we can look at, and the surface would be the 0 on this scale. Distance from the surface would then be measured from there. You can see that high selenium vapor fluxes gives us the highest vacant zinc concentration as you expect, and obviously lower. So everything is quite consistent with that. And indeed, we could design lasing using the waveguiding from that dielectric contrast I talked about earlier from these single wires, and we could tune using annealing the color, the emission color of those wires. All right, so that was the first thing I wanted to talk about. The second part of this optoelectronics piece was regarding detection of light, not emission but detection. So here's a bunch of examples for you of work we've done on making photodetectors, photoconductive detectors, and what you can see is, unlike normal traditional detectors where we're talking about amps per watt as a normal number, if we look, for example, at the zinc oxide one at the bottom there, you can see that we can have some numbers like millions of amps per watt from or close from these wires, and that's because the gain is very high. And what's happening, and we're going to come back to that, is charges get selectively trapped in these structures, which means that the lifetime of the other charge is essentially indefinite, and we get very high gain as these secondary charges are circulating effectively indefinitely around the circuit. The last part of this optoelectronics thing is a couple of things I want to talk about would be time response. And if we look here, we can see that we've done, this is terahertz based spectroscopy, and we can look at the defect based band, and we can tune that to get picosecond response very nicely from these structures. We did that both for the selenium rich and also for the zinc rich, where it's just a state band filling controlling the lifetime. So this whole idea about tuning the structure to tune the response. The last thing I want to talk about here is this idea that we can also have wires that are not independent from each other but dependent, and they form a collective response. So that is the movement of charges in one wire effectively affect the field, sort of like a dipole interaction of adjacent wires and so forth, and rather like a photonic crystal, and we'll talk about that in a second, we can form a grating type cavity structure where the overall structure has resonances where there's higher Qs. And we did this this is in the case of silicon PIN structures, so now we're looking at separate absorption and gain type structures that people use for PIN type photodetectors, and these can be used for single photon counting as well, by the way. But in our case, what we were interested in is the fact that by tuning the spacing and width of these structures, again, we could tune the color response. And so you can see the second figure at the bottom, you can see the color response, but in fact we can tune effectively indefinitely over because we've developed color matching functions over the whole of that XY color space. All right, so that's the end of that second topic on the kind of optoelectronics applications and interest in wires from our end. I now want to talk a bit about sensing. And I'm going to start, and we're going to have sort of biosensing and stuff like that as one of the applications. And the idea is, we're focusing on ultra low concentrations if we can look at single molecule level sensing. So in the case of the first type of sensors, the optical ones I'm going to talk about, we're looking at a change, a binding, if you like, which will change the optical response, and that's the transduction we're looking at. In the next set of sensors, we're going to be looking at a binding, changing the electrical properties, and that will be the transduction we'll talk about there. So this is the case where we've got these nanorods or nanowires in a cavity structure, and I'll talk about that in a second. And why do we want a cavity structure? Well, because if we're trying to detect very, very low concentrations of analytes, then the idea is in a cavity the light lasts a long time. It bounces around many, many cycles, and so it keeps on sampling the same low concentration, and so we effectively have a higher concentration. And there's two ways in which the binding of, for example, a biomolecule on the surface of the structure would change the optical response. One is by changing the refractive index, and remember it's dielectric contrast that's controlling the modal structure in these cavities. So by binding something to the outside of these rods, we change the refractive index, the effective refractive index of that medium. And so if you look at the left figure bottom, you'll see that the peak has shifted due to that refractive index change, with the peak width obviously reflecting the cavity Q. The other thing is that, of course, that material can absorb the light circulating in the cavity, which means it will damp it, so that there's an optical loss change which is pulling down the signal. So the general signal one sees is a combination of those two. All right, so here is the kind of structures that we've been looking at. And the way we did it is we are looking at trying to control adiabatically the way the modes spread in the cavity region, the core region. And we did that just like you do in a traditional fiber optic system, with a wall and a core. And the wall has a different period structure, different spacing structure to that of the core. And clearly the way light propagates in the core will depend, in K-space, will control the group velocity of those various modes we're looking at and so forth. But I'll kind of cut to the chase that these structures enable you to have very high Q modes with Q values in excess of 10 to the 5. And so what that means is when we look here in this next slide on the left, you'll see that the peaks have are very, very sharp, very narrow. So that means that any change from an absorbent on that peak is going to be seen. And to show you the effect of a small change in refractive index, you have different refractive index media changing the contrast in the cavity, and you can see very dramatic changes of the order of 350 nanometer per refractive index unit. So these are very sensitive sensors that can detect, therefore, very small concentrations of analytes. All right, so the next thing in the optical domain I wanted to talk about is it doesn't have to be a linear response. Non-linear effects are also very strong in these kind of nanowire structures, and part of that is the polarization anisotropy due to the way refractive index is set up in these structures, and also part is due to the way charge is distributed. And we go back to the screening and surface state occupation here, which means that one has, in this case, very strong nonlinear response. And in the second pane, you're looking, if you want to call the PL is like the linear response. If you look at the second pane, we're looking at nonlinear microscopy, second harmonic generation. And what we're looking at is the very large Chi2 susceptibility for these wires. And in terms of that anisotropy, which is very interesting, if we have the laser polarization perpendicular to the nanowire as shown in the first pane on the right, you see that that bottom left wire lights up. And if we rotate it 90 degrees, you see that the wire at 90 degrees rotates up. So that we can see that strong anisotropy too in these systems, which can also be used in sensing. So these are interesting approaches where one could decorate or bind to these nanowires as means for harmonic type microscopies. All right, so that's the end of my discussion of optical paradigms within kind of the nanowire regime for sensing, what we've looked at. Now I want to talk about a different approach, which is the electrical approach. And the idea here is shown in the top right figure insert. What we're looking at is we're looking here at a particular single nanowire, and that single nanowire is disposed between two gold contacts, and underneath that structure is a silicon dioxide on degenerately doped silicon base. So that's an FET, a field effect transistor. We can modulate the channel conductance by modulating the potential applied to the silicon backgate, and we can measure the conductivity as current flows through the nanowire. Now, this data I'm going to be talking about will be for indium arsenide nanowires, and those nanowires have surface states or donor-like surface states which are resonant with the conduction band and are generally occupied to form a two-dimensional electron gas. And in fact, very early on, a lot of the power amplifiers, FETs and so forth for microwave type communication were all kind of based on using this two-dimensional electron gas for that. Here in the case of nanowires, the surface states themselves can be occupied either directly or through border state type occupation. And looking on the left, you see a trace of conductance fluctuations, random telegraph noise. What you can see is that the conductance is fluctuating between apparently two states, a lower state and an upper state instantaneously. And in order to prove that to you those are two well-defined discrete states, if you look back to the figure on the right where it shows conductance and the number of occurrences, that's a plot where for each conductance line or level shown on the left-hand axis of the other plot, we count up how many occurrences there are, and we do that all the way across the diagram. And then you'll get a Poisson distribution that is as shown on the right, showing two well-defined discrete states. And the electron transition from one state to the other is what we're actually looking at then. And indeed, because of the sensitivity to local charges, that transition from one to the other can actually be used to pinch off or shut down the transistor. And much of it is due to weak or ineffective screening that I spoke about earlier. And this is taken from a paper we put out in Nature a while ago. What you can see is that you can establish a charge sensitivity for such nanowires. So we can use those fluctuations to measure charge. Right? And on the left-hand axis of the figure on the right, you see the charge sensitivity in units of electrons per root hertz. And the best sensors for charge are single electron transistors, which operate at helium temperatures. And they have sensitivities which are about, under an order of magnitude better than our wires. But the difference is our wires are running at room temperature. And at room temperature, the only alternatives for decent quality sensors would be nano-electromechanical systems, things like cantilevers and so forth, which have 4 or 5 orders of magnitude worse sensitivity. So you can really see that this is an exceptional that these wires operate as exceptional charge sensors. So I wasn't intending to talk to you about charge sensors. I was intending to talk to you about sensing molecules. So the question is, can we transduce a molecular signature to a charge response and effectively take advantage of this? And that's what this last part of the talk is about. So in this case, we decided we would take not just one nanowire, but we'll take an array of nanowires, again disposed on a degenerately doped silicon backgate structure with thin oxide. And these are contact printed down on that structure with two interdigitated electrodes, gold electrode structures. So now we're looking at many nanowires. And so we average that signal out. And the conductance, as usual, is measured as the source drain current over the applied voltage, the source drain voltage for a given backgate. And we define the sensor response now as that conductance against that when there's a analyte present. So the deviation effectively is the sensor. The relative deviation is what is giving us the sensor response. So as an example, I'm going to talk about physisorption of ethanol on these nanowires, and you'll see that we can go over a range of concentrations and we get a nice well-defined response function from these sensors. I need to take a few minutes here just to deviate and make sure that you're aware of isotherms. So a very zero order look at that. If it were a single monolayer adsorption process, we would use the Langmuir isotherm, in which the amount of absorbed material, Nm, is given as a function of its exposure. And so that exposure is done in terms of the partial pressure to the saturated pressure at equilibrium. And obviously, once we reach the saturated pressure, equilibrium pressure, then that monolayer is formed and you have this curve flattening off as shown. On the right is the multi-layer absorption process, which is the normal process one would expect in the BET model, where we have absorption that's occurring over many lengths, typically a few monolayers at least, and the curve for that is shown at the bottom for this multi-layer process. All right, so let's go back to the data that I showed you for the ethanol adsorption, physisorption process. So the sensor response is shown on the left-hand axis, and the partial pressure of ethanol in ppm is shown on the horizontal axis. And we define some parameter x, which is that ethanol partial pressure in relation to the saturated equilibrium pressure of ethanol. And in these experiments we're looking at here, a few ppm would correspond to 10 to the minus 4 or less for that value of x. So when you put that back into the BET isotherm, you see that that isotherm becomes a very simple equation, which means that the number of adsorbed molecules is basically going linearly with the exposure. And indeed, that linear fit works very nicely for relatively large concentrations or exposures, as shown on the scale of this figure, actually, this ppm scale figure. It fits very nicely to that data. Okay, and what's going on? How can we explain this behavior? So what we're talking about here is, in this model, is a kind of uniform dipole layer approximation. And that is that you can imagine these molecules sitting and forming a sheet. And what's the condition for them to form a sheet, as if it's a fixed dipole potential, would be that the separation between the molecules is less than that screening length, which we've already said is very large. So at that point, it looks like it's an additional dipole bias. And the magnitude of that dipole bias would go with the, or the dipole potential would go with the magnitude of the dipole. So could we use, and this is previously published work, we put out a paper which looked at predicting the dynamic and steady state characteristics of nanowire transistors. Could we use such a model? And what's it based on? Well, it's based on a continuity equation with the density of states appropriate for the surface states in there, and their occupation, using obviously detailed balance. It's also got in it the equilibrium distribution of charges and so forth, charge neutrality condition, and a proper showing a Poisson type of analysis of the potential in these systems. And with that, you can recover a lot of behavior. So how did we account for this additional dipole bias? What we did was we just assumed it's like another back gate. And if we do that, then we can, with that model, we can simulate the additional gating potential. And you can see the dashed curves on the left figure as completely capturing the key aspects of the dynamics, and also the steady state on the right that we discussed. So we can therefore put together, using that, we can therefore get a very simple model which gets the dipole charge density in terms of the exposure, and we can capture that as a function of the effective gate bias, as shown in the left figure, and then we can create, because of that model and how it works, we can create a universal curve for the sensor response in that high coverage regime. So everything is extremely well defined by that universal curve. All the data points fit nicely on it. So that brings us to what I said was the purpose of the exercise, right at the beginning of this section, which is to show if we can come up with paradigms in the nanowire case for ultra-low concentration sensing. And that means single molecule type of level. In that case, we're no longer talking about a uniform dipole layer or sheet of charge. We're talking about individual scatterers effectively, as far as molecules coming in and affecting transport in the channel of the transistor. So in this case, we're talking about the separation between the molecules exceeding the screening length, and typically quite a bit. So we say that D has to be greater than or equal to at least 2L in this case. So how do we model this? Well, we can do a kind of Nyquist argument where we can assume that we can break the nanowire channel into a series of resistors of length 2 lambda, and only when, with some probability, some Poisson type distribution probability, only when one of those segments is occupied does its resistance change. And at that point, its resistance will go to delta R, changed by delta R, which would be the resistance when there's an absorbed molecule compared to its quiescent state. And we go through that, and we can ascribe a scattering rate to the quiescent segment as compared to the change in scattering rate for the adsorbed state, and therefore we can get a ratio of delta R upon R naught, and putting that together gets us the sensor response as a function of occupation of these linked segments, as shown by the equation at the bottom. So in that case, now we're looking not at the left-hand figure, which was the high exposure figure, but we're blowing up now the little square box in the left-hand figure insert in the ppb, not ppm range, which is what you're looking at on the right of this figure. And the total sensor response, of course, is the sensor response due to both of those effects, and you can see that we can completely fit the response. So we can completely explain how these sensors are responding now, right down into the few molecule regime. So what insight? So we can explain it, and it looks like there's a lot of equations and so forth. This is some simple thought that we can come to that gets at the bottom of what's behind this behavior. And the answer is yes, we can. And the way we do it is if you look at the derivative of the sensor response with respect to exposure, what you see is that in the uniform dipole approximation, the curve just goes down monotonously, as shown by the little dashed line, down, which means that there's no improvement when we go to low concentrations. So where's the improvement coming from? Well, in the full model, which I just described, you see that there's a peak at the very small concentrations, and that peak is due to the nanowire geometry, and particularly that very weak screening which you get, which is controlling that screening, and then the onset of the single scatterer type of regime. And that's where there's actually a massive enhancement, which you don't get in any other structure, and that's where these nanowire systems can be extremely useful. All right, so to wrap up, in this talk I was really trying to show a few things. I was trying to show how by controlling the growth of nanomaterials and engineering them appropriately, one has access to quite unique properties. And in particular, I focused on some aspects of optoelectronic response and also sensing response, and showed how when you apply that kind of thinking, one can develop high performance light emitters and light detectors, for example, single nanowire lasers, or ultra high response, high speed detectors and single photon emitters, as well as biochemical sensors. So that was almost my last slide, sorry. And for my last slide, I just wanted to acknowledge all the people in my group, my collaborators, who I've kind of been inferring throughout the talk, and these are the areas in which we've collaborated and they've contributed to this work. And thank you very much for your attention.
Thank you very much, Dr. Harry. It was really a wonderful talk. Just
you.
there are few main points to want to discuss. Akash Srivastava has raised one question. Why zinc selenide based high refractive index prism provide large dynamic range of sensing for surface plasma resonance based biosensor? For example, sample having a refractive index span from 1.33 to 1.7.
Sorry, I didn't quite understand the question. What was the question? Should one use zinc selenide for?
Yes.
For which? Sorry, for what type of sensor? For opticals? No.
He has requested for biosensor.
Oh, for a biosensor. Okay, so I wasn't talking about as an optical biosensor.
Yes.
Okay, so would zinc selenide be a good material to use as an optical biosensor? Okay, so actually the harmonic response work was actually on zinc selenide nanowires, where there's a very high Chi2, and actually also so we've been kind of developing. We were looking at core shell structures as well as just straight zinc selenide nanowires. Core shell with intermediate, for example, zinc sulfide. The reason is that one, as you said, you can kind of control the contrast. The problem is, of course, that when I talked about contrast in the first part, where I was looking at these rods, the photonic crystal rod structure, in air is one thing, in a liquid medium is another. So if I look in an aqueous medium like water, for example, where the refractive index can be as large as 80 or something, then the electric field, if you think in a cavity, is actually not in the wire, but it's more outside the wire. And so when you design modal structures, you can have dielectric modes and air modes, so to speak. So the logic is slightly different depending on how you're going to implement that for a biosensor.
Thank you, Dr.
Harris. Yeah.
Participants, any other questions? Madam? Yeah, please.
Yeah, I think there are no other questions for want of time. Yeah.
Oh, fine, madam. Thank you.
Yes.
Dr. Hari, thank you so much for your excellent presentation. And I request participants to contact through email. Dr. Hari, if you have any other points to discuss, and then you can do it. Thank you, Dr. Harry. Thank you.
It was an
Dr.
absolute pleasure. And thank you for having me again. I do appreciate Dr. Grace too.
Thank you,
Grace.
thank you, Dr. Vasudevan, for
Thank you
joining
very
the
much.
session. Yeah, and thank you, Dr. Harry, for joining the session with your lecture. Thank you very much.
Thank you, Dr.
Lovely.
Nirmala. Thank you. Thank you.
Thank you very much. Have a nice day.
Beautiful.
Yeah.
Thank you.
Yeah. So to the participants and Dr. Judy, hi, this is Nirmala Grace. So we'll leave and come back. We'll join the same session in 3 minutes. So as to enable this YouTube.